So one of the things we're going to use a fair amount throughout the semester is this idea of the lever rule. And this should be something that you've seen before in some of your coursework, but want to take a quick moment here to review the lever rule and talk a little bit about where this comes from. This is one of these concepts where I find it's useful if we know where it comes from, because that equips us with the ability to come back in and sort of rederive it if we ever need to. And so we'll do an example here, thinking about single component vapor liquid equilibrium and how we would apply the lever rule to answer the question, how much vapor exists in a vapor liquid equilibrium system given a certain specific volume of the system. And so we'll start out by considering a PV diagram. So this should be something that looks familiar from past coursework. Sketch out the pressure and specific volume axes. All right, and then so we know that in this single component system, that at low specific volumes, we're going to have a situation where we have a liquid, and then as we expand the system, perhaps in some sort of a piston configuration, that's the common example, but as we expand the system and increase the specific volume of the system, we can cause that single component to go through a vapor-liquid equilibrium region and then ultimately completely vaporize to the point where we have only vapor in the system. Right, and this type of behavior is described by the van der Waals equation of state, for example, which you have presumably seen before as well. But what we have here is basically that at a given temperature, or if we sketch out an isotherm here, the van der Waals equation of state, for example, would tell us that we would go through some sort of behavior that looks a little bit like this. And so the van der Waals equation of state is a cubic equation of state, so we get what we call the van der Waals loop here, where things go non-monotonic. And if we remember from our discussion, this is going to correspond to a situation where, for example, we might have a two-phase system that forms, and this would be part of the broader two-phase envelope that would look perhaps something like this, where we have the critical point located up here. Right, and so this is something we've seen before in terms of thinking about a single component system, and we know that if the specific volume of the system is somewhere along this tie line between the liquid and vapor sides of the two-phase region, then we know we're going to have a two-phase system that exists. And so the question that we're going to ask here, and maybe before we ask that question, we'll come in and remind ourselves that we have liquid at low specific volumes and vapor at high specific volumes, and that this isotherm is at a constant temperature. But we're going to come in and ask the question, if we adjust this piston, right, in a way that we set the specific volume of the system at some value we'll call V star, can ask the question, how much vapor do we get, right? What fraction of the total volume of the system, or what fraction of the total mass of the system, for that matter, is made up of vapor versus liquid? And so to do that, we can use this idea of the lever rule, right? And so what we can start out by doing is saying that if we use our piston system to set this specific volume V star, then we know that all of the liquid and vapor in the system have to add up to this. And so V star is simply the total volume per total mass in our overall system. And this, of course, then is going to be equal to some of the vapor volume per total mass plus the liquid volume per total mass. All right, so that makes sense, right? We add up the vapor volume, the liquid volume, normalize everything by the total mass, and that's this specific volume. Or of course, we could say that this is 1 over simply the density of the system, right? All right, so what do we do with this? Well, the PV diagram gives us some information about the system that's useful. We know that there is some specific volume associated with the liquid and also the vapor, and we can read those values off of the PV diagram at the ends of the tie line. Now, these specific volumes are for those specific phases, right? If we think about the specific volume of water in the liquid phase is much smaller compared to the specific volume of water in the vapor phase, or 1 gram of liquid water is much smaller in volume than 1 gram of water vapor at constant temperature and pressure conditions. And so these are 2 different values, but they're specific values of that particular phase. And so we need to work this into our discussion here. And so, one way of looking at this, right, is to say that our specific volume of the liquid is going to be defined as the volume of the liquid divided by the total liquid volume, or maybe we'll just say liquid volume here to make that a little bit clearer. All right, so the specific volume of the liquid is the volume of the liquid per mass of liquid. All right, we've got that sorted out there. And we could do the same thing for the specific volume of the vapor. It'd be the volume of the vapor divided by the mass of the vapor. And so we need to make a conversion here using this information that we have from the PV diagram to get things in terms of our V star equation that we've been working on here in terms of just words right at the moment, but we need to start moving toward essentially doing the analysis to get things in terms of the information that we know. And one way to do that is to think about just what the units have to do, what the dimensional analysis tells us we need here. And this is kind of an easy way to sort through this problem. But if we had a situation where, for example, we had a ratio of grams of vapor relative to the total mass of the system, or grams of total material in the system, then we could multiply that times the specific volume of the vapor, which we know from our PV diagram. And this will give us volume of vapor per total mass of the system. And so that's useful because that's what we want from this previous line. And we could come in and do the same thing for the liquid. All right, and so we know then in this case that this is simply equal to our specific volume of the vapor, and we can say the same thing for the liquid side of the equation. And we could come in and define fractions, a mass fraction of vapor, a mass fraction of liquid. We're going to do that here using x and y. X and y show up all over the place, so we have to just be careful about our context here. But in this case, y is the mass fraction of vapor that exists in the total system. At some point, we'll use x and y to talk about molar mass fractions within a system, but here this is how we're defining these variables at this point. Now we can also look at x and y, and we can realize that if we add x plus y, those have to sum up to 1. That's our straightforward mass balance for this system, or the mass of vapor plus the mass of the liquid has to equal the total mass of the system. And so this then sets us up with a situation where we get y times the specific volume of the vapor plus x times the specific volume of the liquid and we can come in and solve that for y to answer our question of how much vapor do we have at this particular condition. And if we go through and use our material balance here, x plus y is equal to 1, you should be comfortable convincing yourself that this is the result that we get, which starts to look a lot like the lever rule that we've talked about or that you've seen in the past. And so this works well with volume, it works with moles, it works with mass. We'll see this throughout the semester, but we can use this lever rule to answer this question about, how much of the two different things do we have that are on either end of a tie line given some value that's in the middle. And in this case, V star, the specific volume of our actual system, right, is the volume in that piston. And then using the information about the specific volumes of the liquid and the vapor, we can come in and do some dimensional analysis that shows us that we can get this lever rule relationship that tells us about just how much vapor, the mass fraction in this case of vapor, that we would have under these particular conditions. We'll point out too here just before we sign off that, again, remember that this system, if we set the temperature and we set the specific volume such that we get this tie line, right, the pressure of this system would be given over here simply as P star. And remember that basically what this lever rule is doing is telling us something about the position of V star in between the specific volume of the liquid and the specific volume of the vapor. And we see that here from both the equation, and we can think about that in terms of the tie line position as well. We're sort of looking at the ratios of the two different lengths that we have set up by the numerator and the denominator in the equation. So just a brief review on the lever rule for a single component system where we're dealing with vapor-liquid equilibrium. We'll come back and talk more about this as we move on into multi-component systems where we're dealing with VLE, but just wanted to take a minute to remind everybody about how we ultimately get to and do the analysis associated with the lever rule.